Yes, here we are once again. It's the physics video lecture, Physics 190 video lecture 5. So I have some decent notes today, and we have a great topic, the Koshi integral theorem. And I'm going to go back to the semicircular integral we calculated last time and the Darboux inequality, and just look at it a little closer. So let's write here, recall, we looked at dz over z squared, and we estimated it, and we found that for the, we'll call this the contour, for the contour radius r semicircle here, let's say from A to B like that, we found that that was bounded, and when r went to infinity, that magnitude of this thing went to 0 as r went to infinity. So I just want to have a closer look at this thing, because what we did was, since we were on the semicircle, we had z is equal to r e to the I theta, okay? And dz was equal to I r e to the I theta d theta. And so let's just look at that geometrically to make sure we understand it completely. So we know that r e to the I theta is just a circle in the complex plane. If theta goes from 0 to 2 pi, you go around the entire circle. Okay. And we have theta goes from 0 to pi, and therefore we have the semicircle. So let's go ahead and draw a picture here. I'm going to draw a pretty large picture so it all becomes clear. So let's just say we're in the first quadrant. This is the complex plane. Well, let's call that y. It's the complex plane here. And we're out at a point, there's theta. So if this magnitude here is r, then this is r e to the I theta. Okay. Now let's look at dz. We have I r e to the I theta d theta. So r e to the I theta is just z, so that's that point there. Let's write this a little differently. Let's write I e to the I theta, okay, and then we'll write r d theta, because this of course is real. Now what is I e to the I theta? We can think e to the I theta in terms of complex numbers as vectors. That's a unit vector that points here. Okay, that's a unit vector, e to the I theta. I times e to the I theta, remember that's e to the I theta times I, which is e to the I pi over 2. So it's e to the I theta plus pi over 2. Multiplying by I just rotates a number by 90 degrees. So this here is a unit vector perpendicular to this one. So that's unit vector pointing here, label it. And then r d theta, of course, is just an arc length. So r d theta, and what that shows us is that that dz really is pointing along this semicircular arc here. So e to the I theta plus pi over 2 is e to the I e to the I theta, and that's that thing here rotated that way. So the dz is really pointing in the direction of the, tangent to the curve the way it's supposed to. And in fact, when I did my, I could call this the zj plus 1, and this the z sub j, And then remember my dz was zj plus 1 minus z sub j when I was doing the Riemann sum. So you see that as well. Okay, the dz. And finally, note dz magnitude over here now. dz magnitude is just rd theta. rd theta. Okay. So this is just making explicit what we've been doing. And good way to practice with your complex numbers. And because dz is just rd theta, it's clear that integral dz is the length, that's a contour C, length of the contour C if you're integrating, defining it like that. So what these things are geometrically very clear in your two-dimensional complex plane. Okay, let's see. I think yeah, rd theta is. I think I covered that there. Good. That's what I wanted to show you. So that goes back to that integral we did here. And what it really meant. Okay, so next our subject is the Koshi integral theorem. So for the rest of this hour, Koshi integral theorem. And I'm going to do this as thoroughly as necessary. We have nothing but time here, right? So, here's the theorem. Suppose C is a contour, and as a closed contour, I better be precise now. C is a closed contour. F as a function is analytic in and on that contour. So I'll draw us we've got a closed contour here in the complex plane. That's C, and F is analytic in and on the contour. Then the closed integral around this contour of f of z dz is equal to 0. Okay. And this, because the complex functions are so tied together, this is going to have huge ramifications. And I'm going to construct my proof, so I want some pretty big pictures here, okay, that I can do my constructions on. So I'm going to make a larger contour. I can start drawing things. Let's see what we have here. Okay, we've got large picture, contour C. Closed. F is analytic inside here and actually on the contour as well. So here's how the proof goes. So I'm going to break this down into a grid of boxes here. And we don't have to do too many. We're just going to make our point. And then let me write down, so C is the oriented outer contour. So C is oriented like this. And then we have these boxes here. So the first thing I'm going to write down is just this integral here, f of z dz is equal to the sum of integrals, right, j equals 1 to n f of z dz around all these individual boxes. So I'm going to indicate these boxes by doing a square, and that's the jth box. J equals 1 to n. So these have all been numbered, j equals 1 to n. You want to draw this large enough, because how is this true here? If we take this contour and go around all of these boxes as oriented, okay, now look at this boundary here. The top box is going this way, the bottom box is going that way. And so adjacent integrals, these are all contour integrals, line integrals, adjacent ones cancel out. And that happens everywhere. These all cancel out. So these are, this one would be, since they're always counterclockwise, that's the orientation. So we go up here, around here, down on this side, over on this side. Okay. So all adjacent sides cancel, and if you integrate all these boxes up, and the outside ones are also boxes, then you're just left with the outside contour, which is the one we had in the first place. So I'll just note adjacent sides, integrals at adjacent sides cancel. So we're just left with the outside contour. Good. So far, so good. So now we're going to construct a function define delta of z and z sub j. And what this is the difference between a difference quotient and a derivative. So that is equal to f of z minus f of z sub j, z minus z sub j, minus df dz evaluated at z sub j. And this z sub j, right, this is a difference quotient. Z sub j is an element of your box sub j right there. Okay, so we've defined this thing, and now let's look at its magnitude. We'll do the magnitude first. Yeah. Note, limit z goes to z sub j, delta of z and z sub j is equal to 0. And we're going to use that because the smaller you make one of these boxes, the finer you make that grid, the smaller this thing is in a controlled fashion. The magnitude of z and z sub j is what we're going to look at as well, and that's just defined as this magnitude here, f of z sub j minus df dz evaluated at z sub j. So this thing can be, we can just say, is equal to delta, and this thing can be made arbitrarily small. So we're given epsilon greater than 0, we can choose to make delta such that delta is less than epsilon. Which is to say, take an arbitrary epsilon greater than 0, you can choose the size of these boxes small enough to make that delta less than 0. Choose the size of box of J such that delta is less than epsilon. Good, so we're going to make use of that. And now we're going to estimate the size of this integral. We're trying to prove that it's equal to 0, so we're going to do an estimate of this thing based on this construction and that function right there. So let's have at it. So first, solve for f of z. I'm going to name that thing up there star. So we're going to solve for f of z. And what do we get? Right, name that thing at the top there star. And delta of z. Z sub j. So we're solving for f of z. We just cross multiply over. We get f of z equals f of z sub j plus delta of z sub j, z minus z sub j plus, right? Yeah. Plus df dz evaluated at z sub j times z minus z sub j. And so this is what we're going to integrate. We've got the f of z, and before I integrate anything, let's just notice what we have here. This is a constant. This derivative is a constant as well. And this is just the first power. Z sub j is also a constant. So when we do this integral, we have integral f of z dz around c is first the sum of these j equals 1 to n, these c sub j boxes, and now we're going to go into here. Sum of j equals 1 to n box c sub j. Now we'll substitute all of this in here. F of c sub j plus delta z sub j, z minus z sub j plus df dz evaluated z sub j, z minus z sub j, dz. Okay, now we have to study these closely because each one of these, most of them vanish actually. So the integral around a box with a constant times dz is 0, clearly 0. Okay. That it has the antiderivative z, and you evaluate in a closed curve, it goes to 0. So I'm going to strike the ones that are 0, goes to 0. This one here as well, we've got a constant times z. The antiderivative is z squared over 2. Okay, everything's analytic. Here you go, a closed contour z squared over 2. You're also going to get 0. So these aren't 0, but the integral goes to 0. So I'm just striking them. And this is a constant times a constant also trivially goes to 0. So this whole thing here is just down to these boxes right here. So let's write that down. We're left with the sum j integral these c sub j's delta z sub j z minus z sub j dz. We've got room for one more line here. So now we're going to make use of our estimate up there. Make use of that estimate. So let's clean this up first of all. So we have equals just what we have left here. So those are j's. Equal j equals 1 to n z sub j delta of z sub j z minus z sub j dz. Now we're going to estimate the size of that integral. So we'll first use the triangle inequality. So now, integral c f of z dz around that contour, the magnitude will be less than or equal to the sum of all of these integrals magnitude c sub j z minus z sub j dz. Okay, so there, we've got a triangle inequality, and we can estimate these individually as well, less than or equal to sum over j integral. So we'll just take the absolute values inside here. Delta of z sub j, z minus z sub j, dz. So we know that we can estimate this as less than epsilon. And this here, actually, let's go ahead. Magnitudes all, it's magnitudes all the way, right? We can do that. This here is going to be less than the square root of 2 times the side of a box. Because if you've got a box, S sub j, you've got 2 points in there, you're going to be less than the square root of 2 across that side of the box. And this dz is now just being along the side of the box, S sub j. And you go around the box, you've essentially got 4 of those. So we've got less than or equal to sum over j. For all of these we have epsilon, root 2, side of the box j, and then we've got 4 sides of a box. So that's the estimate for each of these things here. And let's see what this is. We have 4 roots, 4 times square root of 2, that's just a number. But then we have oh, actually, I'm going to pull these out. So we have 4 square roots of 2 and epsilon, and then we have the sum of sj squared, and this just turns into the area enclosed by the contour. So that's 4 roots 2 area enclosed by c times epsilon. Okay, these are all finite quantities, and this epsilon is arbitrarily small, and that makes our proof. Okay, we chose epsilon arbitrarily small, so this is an arbitrarily small number, therefore that integral is equal to 0. So I'll just put here, but epsilon arbitrary QED, right? Or whatever, however you end the proof. So there's our proof. And we're going to make use of that. Yeah, so this proof is going to have many ramifications. It's really good. Let's see what we've got here. Yeah, maybe I'll put some words here why these things vanish, just so you can add these to your notes. Integral of constant dz equals 0. Integral of z dz equals z squared over 2. I'm just going to write closed curve, closed contour equals 0. So those things all went away fair and square. This is the only one we had to estimate, and we just did. Good. So that's Koshi's integral theorem. Let's see how we're doing for time. I just want to do a couple corollaries to this, and then we'll call it good. So this one's worth studying. This is a very important theorem. We got a reasonably thorough proof of it, but I think is also pretty transparent. So let's see what else we have for us here. Ah, yes. So we have, okay, so once again, f of z dz equals 0 if f is differentiable or analytic in and on our contour. Okay, closed contour. So there are a couple of corollaries to this. First of all, we have the, if we have z sub a and z sub b, we have the path independence of the integral. F of z dz, since it's 0 around the whole loop, if we go one way or if we go the other way, c sub 1, c sub 2. And therefore, we have a well-defined function. So, f of, say, z sub b minus f of z sub a would be any old contour z sub a to z sub b. All right, so we can define, we've got basically an antiderivative here. Well defined because for any differentiable function in and on this closed contour. So any path in this domain from one point to another gives us well-defined, uniquely defined function. So we have that. And the other thing has to do with multiply connected domains. So we have to define what this is. Simply connected domain, first of all. And then we'll talk about multiply connected domains. So, simply connected domain or region of the complex plane. So region R is simply connected, if in that region, you can take any closed curve and squeeze it down to a point. Take a closed curve and squeeze it down to a point without ever leaving that region. So use a curve inside this region R, and you can squeeze this thing down to a point, and you never leave the region. Okay, so simply connected if any closed curve in R can be shrunk down to a point. Without leaving R. Good. Shrink it down to a point without leaving R. So what would be a multiply connected domain? Multiply connected? Question mark. Well, that's a region here with a hole in it. Okay. That's a region with a hole in it. Or it could be, for example, an annulus. Okay. Suppose you had, and your region, I'll just say, your region R is the region between those concentric circles. Okay. Then that's multiply connected. And you could have more than one circle. And yeah. So multiply connected, you've got some parts that are not belonging to that region. Something that's really common here in what we're going to be doing, these regions where there's a part that's excluded. Well, we'll see. They often have a pole in them. They have a singularity. What they'll end up being is there'll be a region that has a point where the function is not differentiable. But if you leave that out, you've got a domain where you have differentiability. Okay, but you have to, because you're not able to go around these things arbitrarily. Yeah, you have to exclude these. Good. So simply connected, multiply connected. Now the way we deal with these is really great. That's what I'm going to end with. Well, let's take a multiply connected domain with an oriented boundary. So it'll be enough to do two. So here's this region here, and it's got these two holes in it. And there may be some singularities in here, but in and on this contour, excluding these, we have a differentiable function. So how am I going to name this thing here? Okay. Let B be the oriented boundary and that means that we go here, but the boundary is in here as well, and these we traverse clockwise. Okay. That's the oriented boundary to this entire region. Integral, I'll just say B here, f of z dz is equal to these three. So here's what we do. We start traversing this thing. Okay. And then we go in here clockwise and back out. And these adjacent sides cancel in the integration. Do that here as well. And then complete the curve. So there's the total integral. And then we can just add those three together. So we have B, actually not going to be equal, so we have B for the outside one, and C sub 1 and C sub 2. Now we have B plus integral f of z dz, C sub 1 plus integral f of z dz, C sub 2 equals 0 by Koshi's theorem that we just proved. So what that's going to mean, though, is that this outside integral is equal to the negative of the two inside integrals, but if you do the two inside integrals counterclockwise, then you get rid of those two minus signs. So the outside integral will be equal to these two inside integrals. I'll leave you guys to write that down because we're going to come back and make use of this many times. But that's how we deal with Koshi theorem. So let's make sure we formulate everything. We had F is analytic in and on B. Let me make sure I label this thing correctly. So B is the total oriented boundary. So I'm going to call this outside one C. So I've got C for the outside, C1 and C2 for the inside ones. B is the oriented boundary that comprises all three of these, okay? So C, C1, and C2. C I'll just write is the outside. Because now we've applied Koshi's theorem correctly. Okay. The function's analytic everywhere here, in and on these boundaries, multiply connected domain. So if we apply it here, these two cuts cancel each other, and then we have the sum of those equals to 0. And the application of this again is going to be the outside contour integral is going to be equal to those two inside ones. Okay. So this is longer than I wanted to go, but I'm still going to, not so bad. Just going to put a couple easy homework problems up. Just to practice this stuff a little bit. Once we get a couple more theorems in, we'll be doing some really nice and interesting integrations. For now, I'm just going to ask you to do the following problems. You know, you could even just leave room in your notes and do them. Wouldn't be a bad thing, because it's kind of integral to the discussion. So calculate, so let f of z equal z absolute value squared, right, which is z star. And our contour C, we're just going to go around, let's make this a little smaller. 1, we're just going to go around here. This is 1, this is 1, this is the square. We're just going to go around this unit square here in the first quadrant. That's our contour. Calculate integral f of z dz. C, around that unit square there. First, check Koshi-Riemann. The function is not analytic, okay? You're going to get a finite number out of it, but check Koshi-Riemann. Trivially, you're going to see it's not analytic. So you actually get a number out of that, and it's a simple number, but you got to monkey around a bit with this thing here, right? So down here, y is 0. You just have x from 0 to 1. I'll just make a note. Your dz is equal to dx right here. Here your dz is equal to I times dy. Okay. Here you're going in the opposite direction, and what's your dz here? Okay. And here as well. So that's just good for orienting yourself in the complex plane, how these things work. And the second homework problem, this is the really interesting one. Calculate integral z, let's go, 1 over z dz, where z is equal to r e to the I theta. In other words, your contour is the entire circle of radius r in the complex plane. So calculate dz over z, and once you've done that, and I could call this c sub r, c sub r. Once you've done that, go ahead and calculate dz over z to the n, question mark, and not equal to 1, integer, okay. N's an integer, same contour, c sub r, that's an r. Very important integrals, easy to do. Okay. So that's enough for the day. You get those, take a good look at that proof, and we have the pieces in place now to do some really interesting work. Okay, see you guys next time.